All right, welcome everyone. This is AI and Big Data in Finance webinar. We are delighted to have two distinguished speakers today. Olivier Scaillet from University of Geneva and Swiss Finance Institute will present his paper on penalized two-pass regression to predict stock returns and time-varying risk premia. Marcelo Medeiros from Pontifical Catholic University of Rio de Janeiro is the discussant. Olivier has 30 minutes for presentation. After 15 minutes, I will briefly interrupt him, and if there are questions from the audience, I will ask these questions. Marcelo has 20 minutes for discussion. Afterwards, we'll open the floor for questions from the audience. As audience, please submit your questions in the Q&A. I will then call on you and during that questioning part. As a reminder, please be respectful with your comments. The presentation and discussion will be recorded and posted on our website. After the main part, we will have an unrecorded discussion where everyone in the audience will be upgraded to a panelist. Olivier, the floor is yours.
Okay, so now it should be okay. So you should see my screen. So first of all, thank you very much for the organizers of the seminar to inviting me to present this paper to in this prestigious webinar series. So indeed, what I will do is I will talk about a paper which is a follow-up of a type of research that has started, I would say, 10 years ago, where we really try to look at factor modeling, but using individual stocks. So really looking at large cross-section and then try to estimate risk premia based on these individual stocks instead of the traditional way, which is using portfolios. Okay, so we try to exploit the heterogeneity that we have in individual stocks instead of looking at aggregates of stock like portfolios. So the paper, as you can see the title, it's a penalized two-pass regression. So it's an IE and big data seminar. So the big data will be the large cross-section, and the AE flavor will be the penalization. And basically, I will explain how we use the penalization in order to select drivers of the factor loadings. Okay, and there will be a predictability exercise. So what we'll try to do is to predict future stock returns, and as you can see, the main goal here is to do that in a time-varying way, and we will really use the action that we find in the risk premium. Okay, so this is a joint work with Gaëtan Bakali, who is a former PhD student, and now he had joined EM Lyon in France, and Stefan Guerrier, who is also at the University of Geneva. Okay. So what is the context? Okay, so just to give you a little bit of background, so to link with the webinar series, currently there is a recent burgeoning literature on using machine learning and penalization techniques in factor model. And if you look at the many papers written by the organizers, you will have a very broad picture of what is going on and see the references there. It's quite a hot topic. And why is it so is why we look at that is because there is many potential modeling choices in terms, for example, of common instrument versus characteristic. How do I model my time varying betas, etc. And because indeed now we have access to very large cross-section and individual stocks. And of course, we have the computing power in order to put that into place. Okay, so the context here, and again, you can see that in papers written by the organizers, you need really a structural approach to big data. So you need to put some discipline, so to some structure to the data that you have, because you have really a lot of information. And our idea here is really to use finance theory for guidance in order to have that type of structure. So this is a motivation. So first of all, what we try to do is to select models, but models which are compatible with finance theory. So we will really use the no arbitrage restriction that is coming from the standard arbitrage pricing theory in order to put some structure on the factor model that we want to estimate. Okay, so this is a first of that we want to do. We want to avoid so no arbitrage ex ante in your model, in the sense that mechanically you will introduce arbitrage if you are not careful enough about how to write the factor model, take into account this no arbitrage restriction. This is the first goal. The second goal is to look at time variation. In fact, you have the choice between a time invariant factor model, so the factor loadings, and so the betas and the alphas will be time invariant, they will be constant, or you can look at the time variation, so time varying beta and time varying alphas, and you would like to see whether you need that or not, okay? And so what do you see in this? And this is really the key table in the paper. So if you look at the first question, select model with finite theory, you can see that if you use a brute lasso approach, you penalize individually all your coefficients, and this is not a typo, you end up with 100% of your model which are not arbitrage free. Okay, so all the model that you will estimate will present an arbitrage. Okay, and of course, this is not what you want. So this is for the first point. The second point about do we need time variation? If you compare the percentage of time invariant model, you can see that if you use our approach, the adaptive overlapping group lasso, so you need only 38% of the model will correspond to time invariant model. And so the complements, so namely 62% of the model, need action, need dynamics in the factor loading. So you will select so common instruments and characteristics in order to model the dynamics of your betas. Okay, so these are the two key points that we have in the paper. Okay, so let me remind you a little bit what we do. So we use a two-pass penalized methodology. If you remember, the two-pass regression starts from a standard factor model. As you can see, the main difference here is that we have subscript little t. So it means that the intercept and the factor loadings will be time varying. Okay, if you believe in the absence of arbitrage and if you believe in the arbitrage pricing theory, you know that you will get a no arbitrage restriction, which will give you a link between the intercept and the factor loading, so between the alphas and the betas. And you have surely seen that asset pricing restriction in this format, but they are totally equivalent. It tells you that the expected excess return on asset I will be the factor loadings multiplied by the risk premia associated to the factor that you have. Okay, and this is exactly the type of stuff that we will use in our predictability exercise. When I have estimated my betas and I have estimated my risk premium, I can predict so my future return. Okay, and this is the link between the risk premium, the nu t, which links the alphas and the betas, and the conditional mean of the factor. So what is a two-pass regression? So as usually, we will have a first-pass regression where we will do the regression in the time series, so asset per asset. We'll collect the estimate of the AIT and the estimate of the BIT, and then when I have my estimate, I can do a cross-sectional regression in order to estimate my nu t. And if I have my nu t estimated, I can also estimate my conditional mean, and this will give me the estimate of my risk premium. Okay, so this is the second pass is a cross-sectional regression to estimate the nu t, and we use an adaptive lasso to select and estimate the driver components of the conditional mean of the factor. Okay, so basically what we do is we rely on the setting developed by Gagliardini, Ossola, and Scaillet in Econometrica. So we start from a factor model. So here, the factors are observable, so they are not latent factor. So we take, for example, the Carhart model or the Fama-French model, so using long-short portfolio. And if you use no arbitrage assumption, at least in large economies, you can come up indeed with the no arbitrage restriction that I have already mentioned and which will be used in the cross-sectional regression. Okay, so now, of course, if I want to bring that to the data, I need to specify my conditioning information, and I have to specify how how I will model my factor loadings and my intercept. So what we will do is we will distinguish between what are called common instruments. So as you can see, they are not indexed by I. So this will be, for example, in inflation or the dividend yield, etc., which will be common to all stocks. Okay, and then you have characteristics, so stock characteristics. As you can see, they are indexed by I. For example, you can use the size of the firm, the book to market of the firm, etc. So this will be characteristics of the stock. Okay, and of course you have a very large choice for the ZT and ZIT. And what we will do is we'll try to use penalization in order to select what are the drivers of the factor loadings among these potential common instruments and characteristics. Okay, so this is a time varying specification. In fact, it's very similar to what we do in the paper with Patrick and Elisa, but the main difference, as you can see, is that we use sparse. Okay, so in fact, what is the idea? The idea is we will start from a time invariant specification, and the idea is to shrink also toward this time invariant specification and to select among the ZT and ZIT what are the important drivers, and we assume that the BI matrix and the CI matrix are sparse matrices of coefficients. So this is the main difference with respect to the initial paper by Goss. Okay, and we also assume sparse time varying risk premia. And so we assume that we have a non-sparse time invariant contribution, so we will shrink toward the time invariant model. So the time invariant model here plays a role of a benchmark model. Okay, so this is the what is coming from the no arbitrage restriction. So if you explicit everything, what do you recognize? You recognize a time invariant model, so time invariant intercept, and then time invariant factor loadings. And here, what do you have? You have, for example, the scale factor part. You see ZT minus 1 and FT. So we'll have bilinear forms in FT. And this will be also the contribution to the time varying intercept. Okay, so it's really important that you incorporate this time varying contribution. Otherwise, so you will introduce no arbitrage ex ante. Okay, so what is, so to create a model compatible with the no arbitrage restriction, you have the following constraint. The idea is that if you select at least one variable in ZT minus 1 in the intercept, you should also have it in the factor loadings. And similarly, if you don't select a variable in the intercept, you should not select it in the BIT. So in fact, you should group the coefficient also in order to avoid arbitrage. Okay, so we come up with a generic panel model where you can also rename so the drivers of the intercept and the drivers of the factor loading so that you get a generic panel model, and this is what we will use in the estimation. Okay, so what do we do for the 2 pies penalized regression? So we select in the first part the BI through an adaptive overlapping group lasso. So the group will really maintain the no arbitrage restriction between the coefficient in the intercept and the coefficient in the factor loadings in order to avoid introducing arbitrage ex ante. And then the second pass will also use a penalization in order to estimate the matrix which drives the conditional mean of the factor. Okay. So in the paper, I will not have time to develop that, but in the paper, we really have a toy model with 2 factors, 1 common instrument and 1 characteristic, really to explain into detail how you build the group. The groups, how you build the group. So you can see here that you have different groups corresponding to these different contribution in the intercept and in the factor loadings. And the idea is that, so this is if you decide to penalize groups, you will have to delete all these group together, all these variables belonging to the group together. Okay, so this is the idea. And this is we list here the 32 possible models without arbitrage ex ante. So all the models which are not in that table, in fact, will present an arbitrage ex ante, and so should be avoided. And so when you do the estimation, okay. So let me skip that. So why is it interesting to do that as well? Also, as I told you, you can use finance theory in order to bring some structure. And here, look at what we have here. So if you compare a brute lasso approach, so where you will penalize each of the coefficients individually and not group them and penalize group, so you see that you will have an upper bound with respect to the number of potential model in the overlapping group lasso and the number of potential model in the lasso. Okay, and you can see that the bound is 1/8. Okay, now you could say, well, 1/8 is not so small in terms of reduction, but typically in the application that we have, the number of groups J will be much lower than the number of variable in the full model of the AOGL, okay, of the ALSO. So, for example, if you compare to what we have in our empirical exercise, you have 5 factors, 6 instruments, and 13 characteristics. And look at the reduction that we have. So you have a reduction of 2 power minus 97. So it means that you drastically reduce the space of a potential model when you use a grouping structure instead of looking at each coefficient individually. So I think this is also a nice benefit of relying on finance theory, and you really help the penalization method in the estimation. Okay. So in the paper, we have some asymptotic theory. We have a new result for the first pass estimation because we are in a random design case. So this is an extension of what is known in the literature, for example, by Percival. And we have also a consistency of the new heads. And so for the second pass, and we have a proof for that. Okay. And we have, of course, a consistency for the lambda hat. Okay, now let me go in the remaining time to the data. So the data, as you can see, we use individual stocks. We have a fairly large number of stock, so close to 7,000. So we look at the 4-factor model of Carhart, and we also look at the 5-factor model of Fama French. Okay, so what do we have? We have the choice between 6 common instruments. So if we remember, these will be the ZT-1, so the common instrument, and we have also 13 characteristics. So these will be the IT-1. Okay. And we also use the same as the well-known paper of Freiberger et al. So this is the table that you have already seen. So if you use a brute lasso approach without taking into account finance theory and the possibility of arbitrage, you can see that unfortunately you end up with all your models which will present an arbitrage. Okay, and of course this is not what you want. What we have done also in the Monte Carlo exercise in the paper, we also show that you get almost 100% of arbitrage. And so when you do a Monte Carlo, so you simulate no arbitrage model, and in fact you end up with models which are not arbitrage free if you use a lasso approach. Okay, and again, so approximately 2/3 of the asset need time variation in the factor loadings for prediction purposes. Now, what we have done as well, and if you look at the literature, it's currently a very large debate. So if I want to model my factor loadings, should I prefer to use ZT, so common instruments, or should I prefer to use characteristics? And this is the percentage of selection in the driver of the factor loadings. And you can see that, in fact, the number here also are much larger than what you have here. So contrary to the common wisdom nowadays, that people say that characteristics are so important when you look at individual stock, in fact, with our result, we show that it's not the case for the driver of the factor loadings. Okay, so I think this is something it's rare, and the explanation is that the common instruments will better explain how the betas, the factor loadings, move through the business cycles, and so through recession and boom times. Okay, what we also find, and this is in line with what we find in the paper with Inez and Hugues in the Journal of Financial Economics. So characteristics are not necessarily paired more often with their corresponding factor. So intuitively, you could think, so if I have the size factor, automatically I should have in the factor loadings of the size factor, the size of the firm. And you can see that it's not the case. For example, if you look at the size, you here have 0.22%, but you can see that in fact it's more often paired to the market factor and not necessarily to the size factor. Okay, so this is also a new finding that we have in the paper. Okay, what we have also found, and this is quite natural, so the longer the sample size, the more action you need. So if you look at the sample size, so these are the stocks which have a history lower than 6 years, and these are the stocks with a history above 50 years. And what you can see that when you have 15 years, you can see that indeed you have a larger percentage of selected common instruments when you compare to the smaller sample size. So the longer the sample size, the more action is needed because indeed you go through multiple recession, multiple boom times, and so on. So what we also did is a predictability exercise. So basically the AOGL performed better than the ALASU. For example, if you look at the reduction in the root mean square prediction error, you can see that the AOGL indeed do better than the ALASU. Okay, I will skip that. Of course, in a predictability exercise, what you would like also to do is to look at out of sample. So what you do here, you can see that I will do my estimation prior to that period. Okay, so I will estimate my model before 2000, and I will use the estimated model in order to predict the future return. Okay, and again, as you can see, the root mean square, in terms of root mean square error, the grouping procedure performed better than the ALASU, and you can also see, and this will be the case. So if you look at the second period from 2010 to 2019, and you estimate the model prior to that period. Okay, so the AOGL performs better than the ALASU. Now, and I think this is also quite interesting because often people only look at a root mean square error or out of sample R square. So this is, I think, a very interesting picture that I don't see often in predictability exercise. So in fact, this is a distribution of the prediction error. Okay, and look at what you have. So this is the distribution of the prediction error when you do the ALASU. And this is what you get if you use the grouping structure based on the no arbitrage restriction. And obviously, so you can see that the distribution under the AOGL is less dispersed than what you get under the ALASU. And this is particularly the case for the second testing period between 2010 and 2019. And you can see that here there is a clear difference between the ALASU and the AOGL. So the ALASU has a very, very wide distribution of prediction error. Okay, and you can see that this is true also, for example, for the second factor model that we look at, for example, the Fama-French 5-factor model. Okay, so usually the AOGL does better. Sometimes it's less clear with respect to a time invariant method, but still most of the time it's doing better. Okay,
Olivier, you have 5 minutes remaining.
Yeah, okay, thank you very much. I'm almost done. So what we also have is an out of sample R square type of exercise. Okay, so and again, if you compare to the AOGL, so often the AOGL performs better than the ALASU. So if you take an out of sample R square type of loss function, okay, there unfortunately the advantage is a little bit less clear compared to a time invariant method. Okay. So conclusion, so what are the main take-home messages? And I want to be really clear about that. So it's related to the recent paper on the topic. So our empirical results show that taking explicitly into account the no arbitrage restriction, so to really use the arbitrage pricing theory and the finance theory, also does help in trade predictive modeling, so of large cross-sectional equity data set with penalization method. So you should incorporate and discipline a little bit your model through finance theory or economic theory. You can do that also, for example, using a type of stochastic discount factor information if you use a stochastic discount factor approach. So a structural approach to big data where we incorporate finance theory improves on the prediction performance of the estimated quantities, and of course, so avoid to have, I would say, a silly model which is not arbitrage free after the estimation, because then you will use, in fact, so in your prediction, in computing your risk premia, etc., something which doesn't make any sense from a finance point of view. Okay, so I think this is something that is quite important to take into account. Now, further application, and we are thinking about that. Of course, if you are able to predict in a better way excess return, we should hope to have a better predicted performance also in terms of gauging the time variation in the risk-reward trade-off. For example, if you think in terms of time varying portfolio allocation, like in a dynamic type of Markowitz stuff, so conditional Markowitz. So because you have a better prediction of the expected excess return, you should in fact do better. And so it should help to improve performance of time varying portfolios allocation when we use predicted excess return as inputs. Okay, so this was my conclusion. So as I said in the paper, we have a simulation study. So we have a Monte Carlo exercise to check so whether what we do is correct or not. And again, also this is because sometimes we have the question, yeah, but you find 100% of the LSU presenting an arbitrage, but this is because of the data that you have. Okay, here, so the goal of the Monte Carlo is to show that it's not the case. Okay, so if you simulate a true DGP without arbitrage, and you use the LSU to do the estimation, you will end up with close to 100%, so here 98% of your model, which will not be arbitrage free. So you will fictitiously build factor models which are not arbitrage free if you use the LSU. Okay, so the main message is don't do that. Okay, and I think that I will close my main message with that. Thank you.
Okay, thank you so much for this fantastic talk, Olivier. Marcelo will now present the paper. Marcelo, you have 20 minutes, discuss the paper. You have 20 minutes for the discussion.
So I should stop share. It is.
Now let me share here. Okay, everyone can see my screens, okay?
Yes.
So first of all, I would like to thank the organizers for inviting me to discuss this very nice paper. And I would like also to congratulate Olivier and his co-authors for putting this work together. It has been an honor to be the discussant. It's a great paper. So let me start with this. Okay? So in a nutshell, the paper proposed a methodology that's a penalized two-pass regression, where we have a factor model with time varying intercepts and factor loadings. Okay, and the first step, the first pass, uses like sparsity for the time variation drivers plus no arbitrage restrictions. Okay, and then the second step is the second pass is like delivers the risk premia estimates, and with these we can predict equity excess returns. Okay, and there's a very nice Monte Carlo and application study in the paper that corroborates the method and the relevance of the method. Okay, so let me briefly go through the model, what I call the structural model. Okay, the structure in a sense that we are imposing economic restrictions to that model. So we have the returns for a given asset at time t, has a time varying intercept and time varying factor loadings. F is the vector of factors, and this vector takes values on Rk. Okay. There's assumption that the idiosyncratic errors is a martingale difference, so linearity is assumed. Okay? And the factors are conditionally orthogonal to these idiosyncratic terms, which is pretty standard. And we have no arbitrage conditions, as Olivier mentioned, that links the intercept with the loadings and the unique vector nu t. Okay, and with that we can compute the risk premium lambda t. So now there's some more structure in the model where the factor loadings depends on global characteristics that Olivier called Z, and firm-specific characteristics that's indexed by I. Okay, so all these matrices here, A is a vector k-dimensional. B and C are two matrices of dimension k times p and k times q. P and q are the dimensions of Z and Zi, and they are assumed to be sparse, okay, in a way that has the number of non-zero elements is small compared to the total number of elements, okay? And so, as I said, Z and Zi are what we call common and firm-specific characteristics. Okay? The authors also assume a sparse time-varying risk premium. Okay, so lambda t loads on the global factors, and lambda naught is a full matrix, but lambda I is a sparse matrix, and ft f0 is also contain no new elements, and f1 is a sparse matrix. Okay, so with these we have the model. I have some comments on this structural setup. The first thing, when we see a paper about big data or high dimension, we think about which dimensions are in fact growing with the sample size. Okay, so with this respect, I see this paper low dimension in this respect, although the big data comes from the fact that the number of cross sections is diverging and is much larger, for instance, than the number of time periods. But the dimension of the variables itself, like the number of factors k and the dimension of the instruments p and q, are assumed to be known, and they are fixed. They are not growing with the sample size, neither n or t. And I think it should be made very clear in the very beginning of the paper. Otherwise, someone that's from this literature of high dimensional models may think that these quantities are also growing. Okay? So related to that in the end, we have a low dimensional model in the sense that the number of regressors will be less than the number of observations that we have to estimate this model. Why we really need sparsity? Okay, so as far as I understood, the sparsity is a neat way to impose the no arbitrage conditions, because the no arbitrage conditions can translate into conditions of a group lasso, of a modification of the group lasso estimator. But this is not clear in the text. Okay, so one may think, why not just estimating the model by reach? Okay, I understand that if you do lasso or adaptive lasso, of course you are shrinking, you are forcing some coefficients to be zero, and if you do not do this in the right way, you are going to violate the no arbitrage conditions. But you can do reach, or even you can do even OLS. Of course, this will be very unstable, but there's nothing that precludes the estimation by OLS. Okay, so I think the paper needs more motivation why sparsity is needed or wanted. Okay. The second sort of comment is that the martingale difference assumption on the epsilon impose some linearity, right? So why not just assuming that the errors are uncorrelated? If you take like Gu, Kelly, and Chiu paper, they found compelling evidence of nonlinearity in asset pricing models. So maybe this is just a technicality, but will make the setup more general. Okay? Another point that I recommend the authors to be clear about is that if we assume that there is time dependence on the returns, the way the model is written, this time dependence comes solely from the factor dynamics and the time varying structure of the intercept and the loadings. Okay, it's not a problem with that, but I think this should be said from the very beginning. So these are comments about like this general structure model. Okay, so but we should move from this structure model to a reduced form. So if we put all these ingredients together, okay, we get this model for RT, where we have a time varying component, timing varying, sorry, component plus the components where you see time variation. Okay, and of course, estimating directly this model is very complicated due non-linearities in terms of the primitive parameters and the quadratic forms on the instrument. So it's pretty complicated. So the solution proposed by the author is very interesting because you can write the model in a simple panel structure where X is a nonlinear function of the factors and the instruments, as Olivier showed us in his presentation. So we turn out that the model is linear in the parameters, but non-linear in the original variables. And the key thing is that the non-arbitrage assumption will impose restrictions on the betas. Okay, so this is quite smart. Okay, and how to estimate these betas? Well, we can do the unrestricted adaptive lasso, just run this regression here by adaptive lasso without imposing any no arbitrage restrictions, or using the adaptive latent group lasso where the no arbitrage is imposed. So I think here is the way, in my view, the sparsity, I may be wrong, Olivier can correct me, but the way I see the sparsity playing a key role here is that with sparsity, we can write the no arbitrage restrictions as a problem that's that can be solved by latent group lasso. Okay, and with that, also it's interesting because the time invariant terms are not shrunk. So only the time varying terms are shrunk. So we have shrinkage towards the constant model. And the author showed that under general high level assumptions, the AOGL estimator converged to 0 for the truly 0 parameters and to a Gaussian random variable for the remaining one. So there is a kind of a central limit theorem kicking in here. So I have some questions and some remarks that the assumptions are pretty high level on the X. Okay, so I really miss more primitive assumptions on the Z's. Okay, so for instance, what are the moment structure of these random vectors? Because the paper generalized the fixed design framework to a random design framework. So I would like to see what are the properties of disease? So are they time dependent? They are alpha mixing, for example. Okay, so assumption B1 in the that's used to derive the results bounds like X1. So is this expected given the nature of the data in empirical applications? So for instance, in empirical applications, these variables can be highly persistent and non-Gaussian. For instance, take inflation, volatility, or dividend yield, so on and so forth, right? So how these related to these assumptions that we have in the paper. Another point is how to deal with unbalanced regressions, because monthly returns are not very persistent. On the other hand, what you have on the Z's and in consequence on the X's can be very highly persistent. How to deal with that? So it seems to me that the proofs are kind of assuming very strong conditions on the axis, but these conditions may not be satisfied in empirical applications. I think the author should discuss a little bit more about that, okay? Again, the whole of sparsity. So sparsity is not key to derive the result. So I think it's just a matter of using the estimator, but to prove the estimator consistency, sparsity is not necessary from what I see in the proofs. And one question, of course, what happens if we estimate the model by reach? So we are not setting anybody to 0. So what's going to happen? Are we going to violate the non-arbitrary conditions? So it's like more an agnostic approach about these conditions, see what the data will tell, okay? Another thing, although model selection consistency is not derived in the paper, but this could be a nice additional result, especially if we want to like interpret which kind of variables are being selected and which variables are not being selected. It would be nice to have model selection consistency, maybe for this, not for this paper, but an additional follow-up result. Okay? A minor comment that sometimes it's difficult to follow the proofs and the results because everything, but in several parts, the authors make a reference to the assumptions in Gagliardini, Uzzola, and Scaillet, and we don't have those assumptions, so it'd be nice to have these assumptions in the appendix, okay? All right, so now let me move to the second pass regression. So it's a very smart way, it's a cross-section regression to recover nu. And also we estimate the factor dynamics by lasso. With that, we can also estimate the risk premium. So under some high-level assumptions and NT diverging, we can estimate nu and lambda in a consistent way, okay? So comments, of course, sparsity again. And in this case, why we need sparsity on the factor dynamics, right? Because in why not just, because we have a small number of factors, so this model is not really big, so why we need that? And of course, one may ask, okay, if you are not interested in model selection, consistency, why doing the adaptive lasso and not just the lasso? Because the adaptive lasso, you have to select these initial weights, okay? And so this is, I think, the paper should have more discussion on that. And also about like precision on the penalty parameters, because the authors use the same letter to all penalty parameters. So, and there are many, for instance, in the first pass regression, there are many, several regressions being estimated, and then there's the factor model that being estimated by the factor dynamics by adaptive lasso. So it's, as I think I know the answer. Of course, these penalty parameters are different and for each one of the estimation, but I think it would be nice to make this clear, okay? All right, so now let me make comments about simulations, okay? All the simulations, the idiosyncratic terms are assumed to be normal IID. I'll think about relaxing this assumption on the errors and see what happened, okay? One thing that for me was very curious is that both the adaptive lasso and the group lasso strongly underselect the relevant variables. We have like 28 non-zero parameters, okay? And the models are estimating way less than that. And this kind of looks strange to me. Could be highly correlated variables or smallish coefficients. Of course, we don't need like the beta mean condition in a low dimensional setup, only if you have more variables, more parameters than observations. But in finite samples, smallish coefficients may play a role. So I think you have you get a strong taste in your mouth when you see that severe underselection of relevant variables. Okay. So related to this comment, it would be nice to get an idea of the order of the magnitude of the non-zero coefficients. And this also can help us understand if the RMSEs reported in the paper are large or not, right? But they seem pretty small, but that depends on the magnitude of the coefficients. Okay? The other thing is that the adaptive lasso, in theory, there's nothing that precludes the adaptive lasso to be also consistent. Why the performance is so bad? Because the sample is too small for the method to learn the no arbitrage restrictions. Okay, so because this is kind of unexpected. Okay, and a minor comment that the mapes in table 3 seem quite similar. I think we should include more comments on that. Okay. Sorry, here's not comments on the simulations, but comments on the empirical illustration. Okay, so the first thing is that very different relative performance depending on the sample considered. If the sample ends in 2009, or if the sample starts in 2009 and go until 2019. Okay, so a question is do we have a structural break in the data, or is just the size of the estimation period that's growing? And then you have more observations to estimate the model. It would be nice to keep the sample size, the in-sample size the same, and see if we get the same differences in the relative performance. Okay. The other point that called my attention is that the lambda T new model, that's a restricted version of the time varying model, seems very competitive, especially during the first subsample and out of sample. Okay, so again, is this related to potential structural breaks or just the size of the estimation period? Okay. And third, one question that a curious reader might have is, okay, we have this paper by Gu, Kell, and Chu, where they found that nonlinear machine learning methods like random forest and deep neural networks predict returns pretty well. How these compare with this more structural model, okay, that's linear but impose these non-arbitrary conditions? It will be interesting to see. Of course, this would be another paper, but I think it's a comparison that's interesting. I'm about to finish, so some general comments. Also, the paper will benefit from having a guide to empirical implementation. There's a lot of notation in the paper, and if someone is a practitioner and wants to implement the method, it would be very nice to see a step-by-step guide on how to implement and estimate this paper. I think it'd be nice to position the paper with respect to this recent literature on factor zoo. Okay, because here you're considering a small number of factors. Also, there's a literature on the projected and instrumented PCA where factors are in fact not observed, but where the loadings can be time varying, and also to compare and to position the paper compared to these alternatives. And an idea, making a kind of a shameless self-propaganda, I have this paper with Ricardo Mazzini and Jiang Fan, where we bridge factor and dense models, and we can use this setup with your setup on imposing non-arbitrage conditions. And an idea that came to my mind is to combine both things and use our estimator with the no arbitrage condition and see what's going to happen. Okay. And finally, of course, this is a great paper. Congratulations, and it has been really an honor to me to discuss it. Thanks a lot.
Okay, well, thank you so much, Marcelo, for a great discussion. At this point, we have time for questions from the audience. As of now, no one posted a question, so if you do have a question, please write the question or raise your hand and we'll be able to call on you. In the meantime, Olivier, would you like to answer
Yeah, so thank you very much for the great comments. I totally agree that in theory we don't need sparsity. We would need that if we want to have some normality stuff or some indeed selection results, etc. So for the consistency, we don't need it. No, I was more thinking about if you don't assume sparsity. Well, the idea also of the paper is to see whether you need to shrink toward the time invariant model or not. And what we see is that on 2/3 of the model, you don't shrink towards the time invariant model. No, indeed, the structural model P and Q are fixed. I totally agree. Now, be careful, because when you introduce a no arbitrage restriction, what you end up is with a lot of explanatory variable, because you have all these cross effects, etc. So if you look at the reduced model, the number of XIT that we get in our model with 5 factors is 219 explanatory variable. So I think that an OLS will be very, very difficult to implement, because you have, and on top of that, you have a lot of collinearity and that type of stuff. So I think it's a bit difficult to implement. No, I totally agree with the problem of missing at random. So the unbalanced panel, the ZT and ZIT indeed are sometimes persistent. We are fully aware about those restrictions. I don't think that the ridge, I think that the ridge will run into the same problem. So if you say, okay, I use a brute force, a ridge on my stuff, and I don't take into account no arbitrage restriction, you will end up also with a problematic model, because you don't link the coefficient together. So my guess there is a ridge regression will give you the same nightmare in terms of models which are not arbitrage free. Model selection, I totally agree. Too small, yeah, okay. So about indeed the difference between the two out of sample exercise, this is exactly what you say. So it's not a question of the sample size, but it's because of the structural break. So indeed, the 2 periods, so the testing periods behave totally differently, and indeed, this might explain why you see so many differences.
Can I make just a comment here? If you look at that table where you have month by month, the last one in the first sample, the performance really bad. So we are talking about December 2009.
9, exactly.
I think it was like the last one.
Yeah, yeah.
But the first one from the second subsample with January 2010 is really good. So if this is a structural break, is a pretty sharp break.
Yeah. No, exactly. No, this is indeed correct. No, otherwise, yes, thank you for the other comment. These are the main one that. But indeed, the sparsity is really because, well, as I said, so the main motivation was to because you have that debate, and we have that coming from referee, yeah, but we don't need action in the betas. A time invariant model will be perfectly fine. I don't see why we need to model these factor loadings, etc., because we know that the time invariant models perform very well. And so the idea was really to shrink toward the time invariant, see whether you need or not those type of extra dynamics, and I think that what we show is that if you have a small sample size, time invariant model will be perfectly fine. But as soon as you have a very large sample size, then you need some action in the factor loadings, because you have multiple recession, multiple booms, etc. So I think also this is one of the message of the paper. And so typically, if you have a fixed T approach, you can stick to a time invariant model. But if you have a large T approach, I think that you need action in the factor loadings. At least this is what we say.
Yeah, but what my point is, can you just use the shrinkage, because you are not using explicit the sparsity in any of the proofs, right? So you don't need.
No, I totally agree, but it would be
you don't
to say I'm assuming that all these matrices are full.
It could be or not. So
but I still
you kind of you can test sparsity.
Yeah.
So in a way, you can test sparsity. The only thing that someone maybe while you can test sparsity is that when you have the true model, you tend to underestimate the number of relevant variables.
Yeah.
Because you can say, okay, I'm agnostic about sparsity. I don't know if it's sparse or not. In my setup, I don't need it. I'm shrinking. I'm inducing is sparsity in a way, but I let the data speak, right? So, but the problem is that the approach is like kind of maybe over penalizing. I don't know. Maybe it's the way that the penalty parameters are being selected by the AIC. Yeah, could be. Anyway, but these are kind of really details, right? So the paper is pretty cool.
Thank you.
All right. Well, thank you so much, Olivier and Marcelo. We still have a few minutes. Markus has a question. Markus, would you like to ask it?
Yes. First, thank you so much for the great paper presentation and discussion. So I have some comments about the empirics, and you might say these are cheap shots. But my point is you're trying to make general statements, what you learn from your empirical exercise. And then I want to question, is this really the case, or does it depend on choices that you have made? And I mean, all your economic takeaways are subject to the choice of which factors you use, how you transform your data, which means characteristics and macro variables, and what characteristics you put in. And I mean, Marcelo mentioned some parts, but I just want to be clear here, right? When we think about nonlinearities and the loadings, well, of course, if you have a linear model, you can account for some of that stuff depending on how you transform characteristics. To me, it wasn't clear what you did. I mean, if you use raw values, if you use centered rank quantiles.
We do, thanks.
Right, but in any case, right, I mean, I don't see a reason why you couldn't choose like decile indicator variables, you know, some kind of transformation that is a cheap way to do nonlinearity, but it might already capture some stuff. Obviously, when it comes to interaction effects, that is really hard to do in this setup. There are better ways to deal with it. Anyways, but another point is, that's also a generic point, not just subject to what you're doing, but it's common to throw in macroeconomic variables and say, now it's conditional on the state of the economy. I think state of the economy depends on economic dynamics of macroeconomic variables, depends on if you have a sequence of positive movements or negative movements. That's what tells you if you're in a boom or recession. Some of the variables, that was my impression, that you throw in, are not really telling you the state of the economy. They're a combination of a shock maybe and somewhat of a dynamic, but it's, I believe, you need dynamics overall. That means more lagged variables and a time series model to make this type of statements. And when it comes to the factors, I mean, everything you're doing seems to be subject to you believe the Fama-French 5 factor is right, but you don't know how the loading should be modeled. I mean, again, I think there are a lot of people in the audience here that have different stands on which factor model to use, etc. But in particular, when it comes to individual stock returns, my finding is that momentum reversal type factors are quite important, because there are a lot of price trend behavior. And if you omit a factor, it would also render some of your analysis invalid, right? Omitted variable bias, etc. Then another, so this was a point about, you know, things are subject to constraints, and that's, you can take it or you can make comments in the paper. It doesn't affect your theory. But there's one part that's more related to the theory here. And whenever people talk about sparsity, my view is, well, you can have a very non-sparse model in the original space, but once you rotate the data in some right way, it becomes sparser. So if you have a lot of correlated characteristics, if you do a PCA rotation, quotation mark of the characteristic, maybe sparse is good. But so to me, it's not clear what is going on here. And that comes back to Marcelo's question. Do you assume sparsity? What does sparsity mean here? My takeaway from both what I've heard is that your penalty, your shrinkage penalty, is not really shrinkage. It is really a no arbitrage penalty. You just enforce a no arbitrage constraint, but you're not really thinking about sparsity per se, I believe. But maybe I misunderstand it. But if you want to push the sparsity story, then I would ask, do you want to talk a little bit more about assumption on sparsity and what is the right form of data for sparsity. It may be a very minor comment. When we do cross-sectional regression, there's usually the problem of near collinearity in the betas, etc. Can that arise in your context, or do you take care of that? Or is this not an issue in your model?
It's not an issue.
It's not an issue. Okay, well, thanks. Okay, these were my comments.
No, thank you very much. So indeed, very, very interesting. Yeah, I totally agree with your different point. So everything is model dependent. It's a structural approach, so it's unnatural. What we could do in terms of so nothing, we haven't done that, but I totally agree that we could put ZT -2, ZT -3, ZIT -2, ZIT -3, and indeed more stuff in that. If we start to do that, then probably, as Marcelo mentioned, that we will need to have the case really high dimensional, okay? Because then you will multiply the interaction between all these stuff, and you will have product of the ZT -1, the ZT -2, etc. And then you are really in the high dimensional case. And indeed, we have not looked at that, but it might be indeed a very good suggestion to have more dynamics, to take into account more the dynamics in the betas. So I totally agree with you.
Okay, so at this point, we have run out of time. So let's take some of this discussion to the unrecorded discussion part. Before we go there, I want to make a short announcement. So we'll have a next webinar on December 1st. Alberto Rossi from Georgetown University will present his work on crowdsourcing financial information to change spending behavior. We will keep you updated on the details and on the discussant. So please stay in this Zoom room. We will upgrade people to panelists, and you'll be able to ask questions. Thank you.